So for now, the 9.2 subtopics. The second condition for equilibrium. Sa ganina, first condition to, so karon second na pod. So at this subtopics, it composes 3 chapter objectives in which first, state the second condition that is necessary to achieve equilibrium, then explain torque and the factors on which it depends, then describe the role of torque in rotational mechanics. The second condition necessary to achieve equilibrium involves avoiding accelerated rotation or maintaining a constant angular velocity. A rotating body or system can be in equilibrium if its rate of rotation is constant and it remains unchanged by the forces acting on it. Manat siya dili mausab. So, mo siya example. There are several factors on determining how effective in opening the door. So, in this figure, the larger the force, the more effective it is in opening the door. Obviously, the harder you push, the more rapidly the door opens. Also, the point at which you push is crucial. If you apply your force too close to the hinges, the door will open slowly. Most people have been embarrassed by making this mistake and bumping up against a door when it did not open as quickly as expected. Finally, the direction in which you push is also important. But the most effective direction is perpendicular to the door. Since we push in this direction almost inspective, so mas maayo jud o perpendicular kuno inig open sa door para mas dali siya ma-open. So next, in the figure 9.6 as shown above, torque is the turning of or twisting effectiveness of a force. So as illustrated here, for door rotation in its hinges as viewed from the overhead, torque has both magnitude and direction. The counterclockwise torque is produced by this force, which means that the door will rotate in a counterclockwise due to F or the force. Note that R is perpendicular distance of the pivot from the line of action or the force. So B, a smaller counterclockwise torque is produced by a smaller force or assigned F acting at the same distance from the hinges, the pivot point. And C, the same force as in A, produces a smaller counterclockwise torque when applied at a smaller distance from the hinges. So the same forces as in A, but acting in the opposite direction produces a clockwise torque. And letter E, a smaller counterclockwise torque is produced by the same magnitude force acting at the same point, but in different direction. Here, theta is less than 90 degrees. So the torque is 0. Here, since the force just pulls on the hinges, producing no rotation. In this case, theta equals to 0. So, by the way, since we tackled about torque, let me define what is torque. Torque, defined as the magnitude, direction, and point of application of the force are incorporated into the definition of the physical quantity. Torque is the rotational equivalent of a force. It is a measure of the effectiveness of a force in changing or accelerating a rotation. So, in the equation form, the magnitude of torque is defined to be torque equals to Rf sine, open parenthesis, theta, close parenthesis. Where T, the Greek letter tau, is the symbol for torque. R is the distance from the pivot point to the point where the force is applied. F is it symbolizes the magnitude of the force. And theta sign is the angle between the force and the vector directed from the point of application to the pivot point. An alternative expression for torque is given in terms of the perpendicular lever arm, which is defined as perpendicular level arm equals r sine theta, so that torque is equals to perpendicular lever arm force, or the F. The SI unit of torque is newtons times meters, usually written as N times M, or the meters. So for example, if you push perpendicular to the door with a force of 40 newtons at a distance of 0.800 meters from the hinges, you exert a torque of 32 newton times meter. So 0.800 meters times 40 newtons times sine 90 degrees, close parenthesis, relative to the hinges. If you reduce the force to 20 newtons, the torque is reduced to 16 newtons times M, and so on. So the torque is always calculated with reference to some chosen pivot point. For the same applied force, a different choice for the location of the pivot will give a different value for the torque, since both R and the sine theta depend on the location of the pivot. Any point in any object can be chosen to calculate the torque about that point. The object may not actually pivot about the chosen pivot point. So for example, torque is either clockwise or the counterclockwise. Nara ka na siya. If the object can rotate about point A, it will rotate counterclockwise siya sa point A, which means that the torque for the force is shown as counterclockwise relative to A. But if the object can rotate about point B, so kaning B, it will rotate clockwise, which means the torque for the force shown is clockwise relative to B. Also, ang iyang magnitude, the magnitude of the torque is greater when the lever arm is longer. So dako siya, dako ang value sa torque kung makuha ang lever arm niya. So longer. And then in figure, next example, in figure 9.7, force applied to an object can produce a torque, which depends on the location of the pivot point, na magdepende ra sa location sa ilahang pivot point. So, in letter A, the three factors are as the distance, ang F man sa force, and sine theta for pivot point E on a body are shown here. R is the distance from the chosen pivot point to the point where the force or the F is applied, and theta is the angle between force and the vector directed from the point of application to the pivot point. If the object can rotate around point E, it will rotate counterclockwise. This means that torque is counterclockwise relative to pivot A. In this case, point B is the pivot point. The torque from the applied force will cause a clockwise rotation around point B. And so, it is clockwise torque relative to B. And now, the second condition necessary to achieve equilibrium is that the net external torque on a system must be zero. An external torque is one that is created by an external force. So, the point around which the torque is calculated. The point can be the physical pivot point of a system or any other point in space, but it must be the same point for all torques. If the second condition, or the net external torque on a system is zero, is satisfied for one choice of pivot point, it will also hold true for any other choice of pivot point on in or out of the system of interest. So note that